Thank you very much for joining us so early in the morning. So the conventional cameras that we usually use in vision applications are based on the pinhole principle. That means that we look, these cameras, they capture a set of rays that all pass through a single point in space, and then this set of rays is cut by a plane to form an image. But of course there are many more ways to see the world than just using a pinhole camera. And if we look at the biological world around us, there are many more eyes out there. And one specific feature of these eyes, which is shown in the diversity of the eye designs, is that these eyes are all very specifically tailored to the specific requirements that the organisms need to survive in the world. So what I would like to do in this talk is kind of take an inspiration from the world of biological eye design and transfer it over to the design of artificial sensors, cameras. So the central themes of these talks, which I would like you to take away from it, is that there are many more ideas of camera designs out there than just a pinhole camera. And if we look at these different eye designs, they can make certain vision tasks easier than they have been so far. And the right way to analyze generalized cameras is not to think in terms of images anymore, but in terms of light rays. That we look at all the light rays that surround us, and by applying signal processing tools, we can determine the best camera that will be the best for our tasks to use. And often that camera design is not always can be measured in how good or accurate the image of the world is that a camera captured, but that we have to see it really with regard to the tasks that we would like to perform. Because, as you can imagine, an image might be very good for recognition purposes, but sometimes you would like to find out something about the depth. A single camera is not enough, so therefore we need to incorporate that into the design process too. So the basic approach that we use is that we interpret a camera as a sampling device in the space of light rays. The space of light rays can be described by the Plenoptic function, where for every point x in the world, we record the intensity from every direction at any time t. And every camera, every image is a subset of this function. And by looking at the different subsets and determining how they influence the task performance or our ability to solve a given visual task, we can determine the best camera for our purpose. I would like to do some definitions. The Plenoptic function is an idealized concept of a complete view of the world. It contains all the possible visual information that is out there. Of course, if we think of in terms of sensors, we know that we will never be able to reconstruct or capture the world with absolute infinite precision. So therefore, I would like to call generalized cameras with the term polydioptric cameras, where we would like to emphasize the notion that these kind of cameras are only able to capture a degraded image of the visual information that is out there due to the finite precision, finite like sampling density, or finite frequency bandwidth of the optical elements. So the polydioptric camera design consists of two different parts. First, we have to ask ourselves, how well can we perform a given task given the set of ray measurements? And what we would like to do is, by looking at the geometry of the space of light rays, we would like to determine the type, that means the subset, and the accuracy of light rays that we need to perform a given task, and how the accuracy and the type is related to, for example, the sensitivity of the task performance with regard to measurement errors. And later I will go into the sampling theory, where we will look at how well a given camera design is able to exactly give us these kind of measurements. And the goal is, at the end, that we end up with a fitness function for camera design, where instead of having to build all kind of different devices and test them out in the real world, we might be able to say beforehand, by simulating or by computing the optimal point of this fitness function, the optimum of this fitness function, to find or determine the best camera for our task before we actually implement it. And the example that I would like to study is one of this 3D motion estimation, where we would like to, based on the changes in the images, we would like to estimate the 3D motion of a camera, which is one of the fundamental problems of computer vision and very important part for anything from structure recovery to navigation. And I will start with like a relatively well-known fact that we can distinguish our ability to estimate the 3D motion, or how sensitive the 3D motion estimation is to measurement errors, in terms of the field of view. We made some experiments in our lab where we arranged 6 cameras looking in orthogonal axes, and we moved it around through the world, and we would like to recover the motion of the camera based on the images. And if we compute the motion of the camera all individually, since they all, as you saw, they all have a relatively small field of view, and we plot the error function where we, for each given candidate translation, we computed the best rotation and best depth, and what you see here on the spheres is the residual of the image measurements. We see that there is no definite minima, where red denotes the points with the lowest error and increasing towards the black. But instead, the minima are distributed along a valley in the space of translations, which we can interpret as, if we have a small field of view, and we have, since we always have noisy measurements, it is very hard to recover the exact true translation, because due to the noise, the minima of this function can wander around in this valley very easily, and this has been known for quite some time. But if we combine the information from all the cameras together into one system, as we did on the right, we end up with an error function which has a very well-defined minima. So we can, and this has been also, the people who work with omnidirectional cameras notice that the motion estimation process problem becomes much better post, and the results become suddenly much better by using those cameras. So we can kind of differentiate cameras according to their field of view. I also would like to look at something else. Here on the left, we have a sequence of a translating camera in front of the scene, the well-known flower garden sequence. And I don't want you to interpret this now as a temporal sequence of images, but interpret it as a camera translating parallel to the image plane. So therefore, we observe the world not just with a perspective image from multiple directions, but also from multiple view positions, resulting in a subset of the space of light rays, as given on the top right corner, which is known as an epipolar plane volume. So what I like to show now is, just to illustrate how the motion of a camera corresponds to basically different subset of light rays that it captures on its way, and how these subsets determine our ability, how we can capture the motion. And here, the example of a moving perspective camera. On the top, we have the normal perspective image sequence. On the bottom, I picked one row of an image and showed how it basically moves through the corresponding light rays. So each, in the bottom part, each of the pixels corresponds to a unique light ray, and this is these are the light rays that the camera captures at each time instant. And as is well known, that the estimation of rotation is very easy, because all the changes in the images are only due to the motion. The scene does not have any effect on those changes. And we see that on the bottom part, that the camera always sees light, or the light rays that the camera sees have also been seen at a time instant before. So by simply matching up these time instants, we can recover the motion. In the case of translation, we have the well-known parallax effect, and therefore the translation is commingled with this depth of the scene. And as we see on the right, it is not so easy to determine the motion directly from the image measurements, because at each time instant we see the world from a different view position, and thus we capture completely different sets of light rays. And to be able to do the matching, we have to follow along the traces that each scene feature traces out in the space, and basically solve the correspondence problem. So we see, on one hand, we're able to compute just by matching images, while on the other hand, we have a much higher dimensional problem where we also have to solve for this depth of the scene at the same time.